So far, we've looked at solubility in terms of this solution, dissolving the solid into a solvent, typically water. What about the reverse process? It is called precipitation, and it is also hugely important as an industrial process, or a chemical process of purifying mixtures, for example, by fractional precipitation. It has some unfortunate effects, for example, and we have mentioned in a previous slide the formation of kidney stones, which is the precipitation of calcium 2+ salts in our kidneys. It also has relevance, for example, in the formation of caves and the formation of stalactites and stalagmites, which is the precipitation of calcium salts in the form of calcium carbonate in nature. Or you have here, for example, how we can use the common ion effect to precipitate a particular compound of interest. And for example, you can precipitate magnesium hydroxide from seawater by adding sodium hydroxide and decreasing the solubility of magnesium hydroxide in the solution, in the seawater. The process of precipitation, or playing with the solution precipitation processes, is also hugely important in biochemistry when looking at protein purification. So, for example, you can precipitate contaminants and by using a protein with similar solubility to the protein you're interested on, and so it stays in solution. And you can then add, for example, a precipitant, typically ammonium sulfate, which will reduce the solubility of the protein in solution and precipitate your protein of interest. We typically talk about salting out, when you salt out a protein. So again, that's playing with the effect of the common ion effect and the process of precipitation and dissolution in order to purify our protein of interest. You can do precipitation calculations and work out if a particular compound of interest will precipitate or not in a particular set of conditions by looking at the solubility at the equilibrium and comparing the reaction quotient with the equilibrium coefficient, with Kc. And as a reminder, the reaction quotient is the equilibrium constant, but when you are not at equilibrium. So it's the same expression, but the equilibrium constant Kc is when you are at equilibrium, and Q, you use Q when you are not in an equilibrium condition. So you work out those concentrations of those chemicals, will tell you Qc, the reaction quotient, and you can compare that with the equilibrium coefficient for that reaction. So if the reaction quotient is greater than the equilibrium constant, then the reaction will go in the reverse reaction. So if you have, let's say, a chemical in solid form and you are looking at whether it will dissolve, let's say it makes, I don't know, a positive ion, and whether it dissolves or not, you work out the equilibrium, well, you find out the equilibrium coefficient for that reaction. Then looking at the concentrations you've got, work out the reaction quotient, which is the same as the equilibrium constant, but when the concentrations are not at equilibrium, and then you compare both values. So if the reaction quotient is greater than the equilibrium constant, then the reaction goes in reverse. Precipitation occurs. If the quotient is the same as the equilibrium coefficient, then the reaction is at equilibrium and nothing will happen. It's a dynamic equilibrium. The reaction forward and reverse will be will have the same rate. And if the reaction quotient is smaller than the equilibrium coefficient, the reaction has not reached equilibrium yet, the reaction will go in the forward direction. Which means there is no precipitation. It will be in solution. The chemical will be in solution. So let's exemplify this way of looking at solubility product constant and whether substances will precipitate or not with an example. So imagine you have calcium phosphate, a sample of urine with contains a certain amount of calcium 2 plus and a certain amount of phosphate anion. Will calcium phosphate precipitate from that solution? And you're giving here the ionic product for constant for the formation of calcium phosphate. So will this precipitation of calcium phosphate will occur in that sample of urine? Stop the video now, please. So again, the first step is to write the equation and see how many ions are formed. So if I have the calcium phosphate, that liberates calcium ions, 3 of them, and the phosphate anions, 2 phosphate anions. And the next step is again to write an expression for KSP from the information I've got from the stoichiometric of the reaction. So it would be the calcium 2 plus ions to the power of 3, because that's the stoichiometric coefficient, times the concentration of the phosphate anions to the power of 2. And from the problem, I know that in this particular example, we've got 1 10 to the minus 3 molar of calcium ions to the power of 3, and 1 10 to the minus 8 molar of phosphate anions to the power of 2. If I do the calculations, that is 1.0 10 to the minus 25. Well, we've got that the reaction coefficient quotient, sorry, is 10 to the minus 25. KSP is 10 to the minus 26. QC is larger than KSP in this case, and the answer is yes. Precipitation will occur because the reaction quotient with these concentrations of calcium and phosphate anions is larger than the solubility product constant for the formation of calcium phosphate.